So while I'm waiting for the last few people to get logged in, are there any questions regarding the things that we covered last week? We've gotten through somewhere between half and 2/3 of the organic chapter information that we are going to cover. So if you have any particular questions about the stuff we've done so far, let me know. I think I've still got at least 4 people that I'm hoping will show up.
I just wanted to say something about the notes that I was having trouble opening.
Okay.
I just tried clicking on that link that you just sent me, and it's still trying to get me to download Microsoft Outlook.
Even the PDF version that I sent you?
Yeah.
I have no, okay, I'm stumped. I thought maybe it was because the original one was in the doc form. I'm really stumped. You might have to call Canvas tech support. Is kind of my first other suggestion. Yeah, I'm not really sure because that's not a problem I've run into before.
Okay, I'll call them tomorrow.
Yeah, I'm really stumped because it's like if it didn't open the dock, okay, if it's not a PC, I can kind of sort of understand that. But if it didn't open the PDF, I'm assuming you have the ability to read other PDF documents?
Yeah, nothing else has been an issue so far. It's just when I click on it, it tries to take me to another website, and it's just a word that says unavailable, but everything else opens up in the Chromebook equivalent to Word, and at my PC computer at work, it's the same thing. Everything else opens up just fine, but that still tries to take me to a website that says unavailable.
Okay. And then I sent you a reply back with a PDF in it.
Yeah, the link that I get here, it's every link you've sent me, it just takes me to another website to download Outlook for iOS and Android.
Okay, now, yeah, I'm really stumped because I'm not certain that I'm not certain that's something that I can fix.
That's fine.
What? Oh, my husband, the techie, says it's a device or a device issue on your end, which is my suggestion of call tech support at the Canvas tech support, and yes, you'll probably get stuck on the never ending hold thing for a while, but they are usually pretty good at resolving stuff. That's the only thing I can think of.
Okay, I'll try that, and if I can't get through, I'll try and have a friend do it on their laptop also. But
Okay,
that's why it's weird because it's not working on Chromebook, and it's also not working on my PC at work.
that makes me think that your Canvas account
Mhm.
has a glitch.
Okay.
That would be kind of, since it's on 2 different devices,
Yeah.
that would be, but it's both, okay, Canvas being the common point between that. That makes me wonder if it really is a Canvas tech support problem.
Right.
Because yeah, every now and again, even before this year, every now and again, I'd have somebody who'd like go, well, it won't let me log in, or it'll log me in, but then it kicks me back out no matter what device I use. So I think sometimes it's a Canvas problem.
Okay. Thank you.
Other than that, the other thing you could do is send me a reminder to my armoller@verizon.net email, and that way we're going outside of the Canvas system, and I should be able to attach, hypothetically, any form of document to the regular email and send it back to you. I don't know if you have a Yahoo account or a Gmail account or something like that I could send it to.
Okay, I'll do that.
That's also another way that we can at least have a temporary work. We have to figure it out eventually because it's tied into the testing system.
Right.
But that might be a temporary workaround.
Okay, thank you.
Anybody else having tech issues? My daughter is the one who's guilty of having tech issues. She has a Saturday class, and she had webcam problems because the class that she's taking wants to. I don't care whether you guys. I mean, it'd be nice to see faces, but I don't really actually care whether you show me your faces when we're doing lecture or not. But the class she's taking, somehow it's they want to show all the people on the Zoom call. So she was having tech support problems with that, trying to get her webcam to work the way it was supposed to. Yeah, we're all a slave to tech issues right at the moment. All right, is that everybody? I think I might be missing one person, maybe, because I have 10 people on my roll, and I see me and 9 other names. So I think that maybe means I'm missing one person. Hopefully they will log in shortly. All right, back to are there questions about the organic stuff we covered last week? We are a little bit past halfway through with the organic stuff. Otherwise, I will pop open my file and we'll kind of pick up in the neighborhood of ethers again. And it would help if I actually hit screen share when I did this. All right, so I think we got down to this one. I think we got as far as ethers. The last bit we were talking about being that if you have your oxygen atom in the center of your ether molecules, you are not required to have an identical R group, an identical carbon containing group on both sides. The left side is allowed to be different from the right side, so it's not a criteria that they actually match. Sometimes they do. The ones here that are shown that match are the diethyl ether one, because it has an ethyl group on each side, and then the diphenyl one that has a benzene ring on each side. So both of those do actually match. All right, moving onward then. So still sticking with the oxygen concept, we're going to do something a little bit different with the bonding. In the groups that are referred to as aldehydes, note there's a double bond between the carbon and the oxygen. In this case, it happens to be above it. You could draw it below. It doesn't actually make a difference. It's like picking up your molecule and turning it over. It doesn't really matter whether the double bond is poking upward or poking downward. So whatever your R group is on one side of the C double bonded O, but the other side has to have a hydrogen. Otherwise, it might not be an aldehyde. There's another word that I can't remember if I actually stuck this in the notes or not. You might run across that the C double bonded O is referred to as a carbonyl, CARBONYL. So you will sometimes see, oops, I'm hopping around between my stuff here. You will sometimes see the C double bonded O referred to as the carbonyl. So I picked, like I said, a lot of this is cut and pasted from various websites. They categorize them into saturated ones and aromatic ones. If you look at the first smallest molecule, this one's probably at least familiar from the name part of view. If you're an adult, chances are you have heard the term formaldehyde. Usually people talk about it as a way of preserving specimens for biological study. It is something that we've actually known about as a substance for quite a while now. Formaldehyde goes back almost 100 years, I think. Okay, slightly diverting from the subject. I am guilty of watching way too much Ask a Mortician on YouTube these days, and what was sort of unaware that formaldehyde is actually still part of the embalming process in preserving dead bodies. So more weird trivia. If you look at the one next to it, you see the cryptic, every corner and every end is where a carbon is. Butanal. This is also a difference between the older naming system versus the IUPAC system. The older naming system ends their words in aldehyde, which is still excessively used by the medical community. If you just see AL at the end, this is the IUPAC version of naming it. So butanal is a aldehyde with 4 carbons. Then we've got benzaldehyde, because it's got a benzene molecule in it, which actually weirdly smells really good. Benzaldehyde smells a great deal like almond extract. Note anisaldehyde. This is another one that has a scent to it. Anisaldehyde smells like licorice. So they're aromatic in more than one way. They're aromatic because they contain a benzene part to the molecule, but they're also aromatic due to their scent. Lots of artificial flavors and artificial scents are made with aldehydes. You see cinnamaldehyde. This is basically an artificial cinnamon flavor. Vanillin is a way that imitation vanilla is produced. So unlike some other organic molecules, the aldehydes often, especially the larger ones, smell kind of nice. Formaldehyde doesn't smell good, but actually acetaldehyde doesn't smell particularly great either, but some of the bigger ones do. So that gives you some additional examples in addition to the ones that are like in your textbook. So what if we take off the little dangling hydrogen that is there on the right-hand end past our C double bonded O and stick some more stuff in there, okay? Another R group. Well, this actually changes our category. They are now known as ketones. And the one that is most well-known, acetone, you see it has the C double bonded O in the center, and it has a methyl or a single carbon group on each side. Acetone is what they put in nail polish remover. That's what makes it break down the nail polish. If we go back to other naming systems, you will sometimes see it referred to as dimethyl ketone. If we go to the IUPAC system, you might see it referred to as 2-propanone, the 2 indicating where the important part of the molecule is on the carbon chain. It's the carbon number 2. Methyl ethyl ketone. This one is sometimes used as an organic solvent for stripping lacquer, I believe. It is also a liquid that has some industrial uses. Then we see benzophenone, sometimes called diphenyl ketone. Note, that one actually has matching parts, okay? The one in the middle doesn't. The one in the middle has a 2-carbon group on the left-hand side, but only a single carbon group on the right-hand side. So sometimes the left-hand side matches the right-hand side, sometimes they don't. what if we tinker a little bit more and take that right hand R group and kind of slide it to the side a little bit and put a second atom of oxygen. Now note, this oxygen is not double bonded. The one there on the right-hand side is a single bond. So you have both a double bonded and a single bonded oxygen in the same molecule. So if we look at some of the more common ones, so methanoic, so single carbon atom, but it has a double bonded O and a single bonded O. If we named it by the older naming system, it would be known as formic acid because it is a cousin to formaldehyde. Ethanoic acid. We don't usually call it that. We usually call it acetic acid. This is one you've seen a great number of times in the first semester, and you will see acetic acid a large number of times this semester. Ethanoic is the IUPAC name because it has that F to indicate to you that it has 2 carbons. Propanoic. Propanoic therefore has 3 carbons in a row, with the last right-hand one being the one where your 2 different O's are attached. And then we have butanoic, which is also known as butyric acid. Butyric acid is awful in terms of smell. Think sweaty gym socks. Butyric acid is really kind of nasty. I remember a particular incident in high school because I took organic chemistry in high school. And I took a watered down version in high school. And somebody spilled the butyric acid. It's like, oh God, turn on all the hoods. Because it really does smell pretty bad. So we've got all these different versions. There's one last version, which is O's only combined with the H's and the C's. And I just realized that I didn't give you a example. Yeah, this goes back to the I thought I had cut and pasted all my examples into it, and I forgot to give you examples. So methyl ethyl ester, okay, which I actually didn't draw out. So let me see if I can do this on the whiteboard. All right, let's do this. All right, we're gonna do, there's my carbon, and we're gonna put a double bonded O on the top. And then we're going to put a single bonded O. So this is the middle of my ester molecule. So I'm going to put a CH3 over here on the left-hand side. And then I'm going to put a ethyl group, a 2-carbon group, CH2, CH3, okay, and this is known, let me see if I can switch over to text here, as methyl ethyl, I hope I spelled that correctly, ester. So you have the double bonded O and the single bonded O to your carbon. There's no H's. There's no H's that are directly attached to the O's. So this is part of what makes it the ester part. And so if I go back to drawing here, okay, I'm going to kind of see if I can, let me draw. That bit there, okay? That L-shaped portion is specifically what helps to make it an ester. All right, let's try something a little different and see if my funky little drawing thing will cooperate here. All right, so here's my ester functionality. And then, da, 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 da. All right, benzene ring. Okay, granted, it's kind of, I know it's terribly scribbly, but that's sort of unfortunately in the nature of the whiteboard. I wish I had a stylus, which would actually write successfully on my little touchpad for my laptop. I've tried a whole bunch of different ones and never had any of them seem to work the way I would like them to. So I'm usually just kind of stuck trying to do it with my finger and dragging it around. But these are esters, okay? So, and there are a couple pictures of esters in your textbook, so go back and also have a look at those. All right, let me hop back to my actual file since I skipped the pictures of the esters. So now we're going to switch gears just a little bit in that no O's, no oxygens for a moment. How about some nitrogens? So back in first semester, we saw the small molecule NH3, which is ammonia, as opposed to NH4 plus, which is ammonium. And NH3 at regular temperatures and regular pressures is a gas that smells bad. It smells like a cat box. But that particular molecule, we can pop off hydrogens and replace them with R groups. So if we look at some of my examples here as we go down, if you replace one of the hydrogens, like the top molecule, this is what is known as a primary amine. This is, again, just sort of information to kind of give you on why things are sort of put together the way they are. We've got CH3, CH2, NH2. So only one of the three H's has been replaced. Okay, what if we do it slightly differently? Next one down, we've got a CH3 group on the left and on the right, and the NH in the middle. So it's a secondary amine. It's a situation where there are two R groups attached to your nitrogen. And then the last one is a tertiary amine. You took away all the hydrogens and replaced them with something else. Now, the examples that I gave you here, again, I sort of fall into the category of, I made them all look alike. They don't have to be. You could draw amines that have differing R groups. And I will mention, just because it does exist, there is such a thing as a quaternary amine. They're actually used in the creation of some medications, because if you have a quaternary amine, you can react it with a chloride and produce a salt, which is often much better absorbed by human systems than things that are very alkane-ish, very saturated hydrocarbon-like. So we got a couple more to cover. Amides are an odd blend. They've got the carbonyl, your C double bonded O, but then they have this nitrogen attached to it. So it kind of looks like you mated a ketone and an amine. Amides are unbelievably important for living systems. Amides are what allow you to form proteins because the amide bonds are what hook your amino acids together. So you see a kind of a generic-y version there that says the left-hand side can be an H or it could be an R. You've got your carbonyl and your nitrogen, and then you've got the two spots on your nitrogen that can have something attached to it that can be more R groups or they can be hydrogens. And then I gave you two smallish amides there, acetamide and hexanamide. Okay, acetamide having 2 carbons, the hexanamide one having 6 carbons because hex for 6. What if we throw something else in? What about halogens? Okay, fluorine, chlorine, bromine, iodine. We're going to pretend we never heard of astatine for right at the moment. Yeah, yes, astatine is at the very bottom of the halogen column. However, from a haloalkane point of view, you are not going to see astatine as part of those molecules. So haloalkanes have actually all sorts of really fascinating uses. Here's a set that predominantly has chlorines in it. Methyl chloride is actually used to extract caffeine from coffee if you don't have organic decaffeinated coffee. Instead of using like high pressure liquefied steam, they use methyl chloride. Isopropyl iodide. Okay, so they stuck an iodine atom there in the middle of that molecule. N-butyl chloride, sec-butyl chloride, isobutyl chloride, all slight isomer variations. And then T-butyl chloride, also sometimes known as 2-chloro-2-methyl propane. Again, I kind of like this particular little table that I found because it gave you the common name, but then it also gave you the IUPAC name. So it kind of gives you a nice little bit of a comparison there. So the last segment of that kind of goes with what we are covering of the organic chapter goes back to the naming. There are some rules. So I'm going to give you a few examples, then I'm going to try to flip back to the whiteboard and give you another one. One of the things you need to think about is name the longest chain. It doesn't matter if your chain has bends in it. You can, metaphorically or on paper, unbend them to make your chain straighter because you want to count the longest possible chain. Give the name and the location of the group, any of the twigs or branches that are attached. Use the lowest numbers possible. If it gives you lower numbers to start counting from the right-hand end versus counting from the left-hand end, do so. And list substituents in alphabetical order, which basically means things like ethyls come before methyls because E comes before M. So let me kind of walk you through some of these examples here. Butane. So it is just a butane molecule because one, ANE, it's an alkane. It has nothing but single bonds. It has 4 carbons. So metheth-prop bute. Bute is 4. It has no branches. So it is a butane molecule, occasionally referred to as an N-butane. And sort of kind of technically refers to as normal, but it also means you just have a straight chain. So look at the next one down. If you only look at the straight part of the chain, it kind of looks like you have a butane again. I don't know if I can use my highlighter to kind of show this to you. So if I do, oh, that didn't work. Let's try this again. Out. Nope. This is being. All right. So if I only look at that part, the part that I highlighted yellow, it kind of makes it look like it's supposed to be a butane. But what if you take the little L that's on the left-hand end? What if you take that CH3 and you actually start counting there? So you do the one that's kind of poking upward on the left-hand end. That's carbon number 1. And then you go 2, 3, 4, 5. So the longest chain is actually a pentane. And then it has a twig in the middle. Well, in this case, it happens to be symmetrical because it doesn't really matter whether you started counting toward the left-hand end or whether you started counting toward the right-hand end. It ends up being number 3. As I try to turn my highlighter off now. It's being uncooperative. So no matter which one you start at, whether you start at the left-hand end or the right-hand end, the twig, your methyl group, is at carbon number 3. So 3, and usually there's a dash, methyl, and I'm not super picky. You can write the methyl as a separate word, or you can squish it all together. As we look further down the page, you will see that a lot of the ones in the lower examples just kind of squished it together. All right, so next one down, the left-hand one. We have a hexane chain, so 6 carbons. And then it has 2 twigs, but one twig is bigger than the other one. The one that has 2 carbons is your ethyl, and your other one is a methyl. So I made it 2-methyl 4-ethyl, which actually then I sort of rearranged it a little bit. So it's 4-ethyl 2-methyl hexane. That way you know where the twig is that has a single carbon, and you know where the twig is that has the bigger carbon chain, which is the 2-carbon chain. If you look at the next one, the right-hand one, 4-ethyl 3,3 dimethyl heptane. So this one, okay, your longest chain is a 7, and then it's got 3 branches. If I started counting at the left-hand end, it would give me 4, but then 5, 5, okay, for my dimethyl. I don't want to do that. I want to start counting so I can get lower numbers. So I actually started counting at the right-hand end of the molecule, and that way I can get a 3,3 dimethyl. Yes, it is okay to have the same number twice if both twigs are attached to the same carbon. Now, another reason I like this particular picture is it gives you a, don't do it this way, here on the third, or the next one on the left-hand side. We have a heptane. So heptane is your longest chain. But if you kind of did it backward, You might be tempted to say 2,3-dimethyl 4-sec-butyl. Okay, that's not optimal. That's not giving you the lowest numbers possible. You're better off with giving it as the 2,3,5-trimethyl 4-propylheptane. So 3 little twigs, okay, 1 big twig. Did I hear somebody make a comment? It did not show me comments.
No, but can you go into a little bit more detail on that one of as to why?
Okay, so look at the numbers that they wrote above the chain. So there's a 1 at the far right-hand end. If you started naming at the other end, you get bigger numbers because you wouldn't start until you actually got to number 3. So they're like going, okay, which way can I do this that will actually give me the smallest number of branches? And a lot of times you have to kind of tinker with it. You have to go, well, if I did it this way, what does it give me? Oh, well, what if I did it the other way? So sometimes it ends up being a comparison. Let me switch back over to my whiteboard. In some ways, not being able to draw circles, okay, on my notes is really annoying.
So it's not something you can just look at and be like, okay, this is how you do it.
No. A lot of times you have to kind of figure it out. All right, so let me see if I can do this. All right, so I'm going to give you a skeleton, and then we're going to see if I can get it to... Okay, this is like not super easy here. So CH3, CH2, CH2, CH3, oops, CH3, CH2, CH2, CH3, All right, now we try the draw thing. Okay, so straight line, straight line, straight line. All right, so we have a kind of oddball looking molecule. So my first attempt would be, well, what if I just circle this bit? Okay, so if I only circled that bit, I've got 1, 2, 3, 4, 5, 6. That's a hexane. Oh, but I've got this little one down here on this end, so I could have actually made a longer chain out of this. So undo. So what if I go like this? Does that give me a longer chain? So 1, 2, 3, 4, 5, 6, 7. Oh, that one's longer. Oh, but then I noticed that this bit over here, okay, that's actually could be part of the main chain. So maybe I actually need to go around corners. I need to go like this, and then here, and then back. Okay, and that's my main chain. So we're going to call this 1, 2, 3, 4, 5, 6, 7, 8. So this is an octane. Okay. And then I got to figure out, well, okay, which end do I want to count from? All right. If I start here, okay, if I started that one and I count backwards to the left, we've got 1, 2, 3, 4, 5, 6, 7. And I've got a twig at 4 and a twig at 7. So I'm going to kind of write something temporary down here. I'm going to put my 4 in my, so 4, 7, something, something octane. Okay. But, okay, what if I counted from the other end? Would that actually give me lower numbers? So if I start over here at this end, okay, and I go 1, 2, 3, 4, 5. Oh, I get lower numbers. Okay, so it would actually be better for me to count from the left-hand end. So I've got a 3 and I've got a 5, and they actually are both the same twig. So it's a dimethyl, and I went 1, 2, 3, 4, 5, 6, 7, 8. So it's an octane. So a lot of times you kind of have to test it out. Sometimes it even takes a couple of goes to figure out what your longest chain is, because you have to sort of metaphorically unkink it so that it straightens out and gives you the longest possible chain that way.
Yeah, that helped me out a lot.
Like I said, being able to draw is actually a really big deal when you're like doing when you're doing organic stuff. So let me go back to my other examples then. So look here at the one with the funky triangle, because we're actually going to see this a little bit of the triangle stuff in lab when we get around to the organic lab. It is a cycloalkane. And in fact, okay, you can't make a circle out of 2, but you can make a very stiff and not very pleasant circle out of 3 carbons. You get a little triangle out of it, obviously. Cyclopropane. In this case, your cyclopropane has a twig. It's a methyl cyclopropane. And then we look a couple of the other additional sort of wonky ones here. We've got 5-sec-butyl, because it's got a really big twig on it. And if I count, actually in this one, it doesn't matter whether I count left or right as far as the sec-butyl is concerned. This is a really symmetrical molecule here, this bottom left-hand one here. Either way, you kind of get a 2 and a 7 and a 5 because they're all alternatingly split there. But then the last right-hand one here, hexane is the longest version you can get because it's 6 across. You have one short twig that's a methyl and one longer twig that's an ethyl. If I name them so that I end up with a slightly lower number on my ethyl because it's alphabetically dominant, 4-ethyl, or 3-ethyl, 4-methyl. And then I picked this other example here, which is from a different source, that kind of shows you the E, the I, and the M, because I wanted to give you an example that had a little bit more alphabetically going on. So ethyls, isopropyls, methyls. some of this, I really wish we did have an easier way to kind of do this better on my whiteboard. I might try to, okay, I have it, okay, I'm a homeschooler, I'm a lifelong homeschooler, but both my kids were homeschooled the entire way. My daughter is now a dual enroll. Like I said, she's taken a class from TCC because she's a high school senior. She'll graduate in May. But partly because of that, I own a chalkboard, a real actual chalkboard, not a whiteboard. And sometimes last semester I figured out a way to get my big kid to help me film in such a way that I could draw things on the chalkboard that made it a little easier to see. So I may have a go at that for a portion of class on Thursday, just to kind of make sure I can give you a couple of additional examples. So this is actually gets us all the way to the end of what we are covering in the textbook. If you go back and you look at chapter 20, one of the things you will notice is that there's actually a little bit of, I'll call it reaction information in the chapter, which we're not going to do. I also think at the very tail end of the chapter, there's a little bit of biochem, which we're also not going to do. So this actually covers all of the information that is covered for your organic chapter. So what this will do is make your organic homework due at midnight on Thursday, which gives me a chance to give you an extra example or two on Thursday during the lecture portion. But because you're going to have to draw some stuff, you're going to, well, you're probably going to have to print out a physical page. Like I said, unless you have a grand and glorious computer that has like some sort of stylus thing that does a much better job than me trying to write on my little, 2-inch square touchpad, you're probably going to have to print it out on paper and draw some of the molecules and then either take a picture and convert it to PDF or scan it if you happen to have a flatbed scanner. I know that there's a whole bunch of apps available these days that will take your picture, which I guess is a JPEG, and then you call it up into the app and it will allow you to convert it to a PDF. I don't think it's super difficult. But that's probably chances are that's going to be what you're going to have to do in order to be able to give me a file that you can attach to Canvas. If you can't get it converted, send me an email. I can open a JPEG through my email, but it'll be easier if you can do docx or PDF in order to attach it to the Canvas.
With the iPhones last semester, if you go through your notes and hit scan, and it'll take a picture of the paper, and then you can send it that way through your notes in iPhones, and it'll send it to PDF.
But okay, question, because I'm not an I anything owner.
Yeah.
Do you have any idea what format does it open in Canvas?
Yeah, because that was the only way that I could send them to you last semester, because if I just take a normal picture, it would send it as a format that you couldn't open.
Okay.
I went through my notes and then scanned the picture into my notes and sent it as a document and sent it as a PDF.
Okay.
Yeah.
All right, we'll get it figured out. Some of you I have for lab. Okay. Not all of you, but some of you I have for lab. So tomorrow we have a Zoom lab, which is about plotting, basically the usage of Excel. which is going to be here on Zoom. And everybody I have for lab will be doing lab via Zoom this week. Because I finally got a schedule from Dr. McHugh. We next week will begin the every 2-week rotation. Let me twist around here and grab one of my pages. So for instance, I divvied my class up into half and half. I have 14 people registered, so I put 7 people in each section, which gives us a little bit of wiggle room if you have a critical, like, I can't make it this week because childcare or something like that. It gives me a little bit of wiggle room. I just can't have more than 12 students in the class at one time. New regs. So my B group people will actually come to campus, the Norfolk campus, up on the 4th floor in the science building to do the absorption spectroscopy lab on the 27th. So not tomorrow, but a week from tomorrow. The other half of my lab people I'm going to make a little video about the organic lab, which has already been loaded. Okay. It just doesn't have a whole lot of instructions right at the moment. That's my project for the next few days, is to make a little video, which I can then attach to lab so that you can watch the video and then you can draw out all the structures in order for lab. And I'm offering 2 options, and I'll talk about this again tomorrow for people who actually have me for lab. You can, I set Canvas to default to digital submission, but if you would rather draw out all of these molecules that you need to for the organic lab on a sheet of paper and actually physically hand me the paper the next time you have me for lab, that's fine too. I just decided I would try to do it reverse from the way I did it last semester, which was I defaulted to paper, but then at the end of the semester I had to change it to digital because that was post Thanksgiving and nobody was allowed to see anybody anymore. So this time I'm trying to do it from the opposite direction, but that means you can still give me paper stuff if you want to. It just will, when you log it in, or when I log it in, it won't look like it has a file attached to it. It'll just be a number value on the grade columns for Canvas. So I'm hoping this is a slightly better way to approach the problem. People who don't have me for lecture, to the best of my knowledge, Dr. McHugh and Mr. Wheaton are also following the same schedule next week. So you may have to double check with them as to how they have divided up their classes. I think Mr. Wheaton only has 11 students. So I have the suspicion he might not use the rotation. He might just see everybody every 2 weeks, instead of seeing half and half. So if you have Mr. Wheaton, you might need to check with him about that particular portion of the scheduling. It's also complicated. I keep wishing that we can get this sorted enough that we can kind of resume reality. So questions regarding homework, I'm gonna when I log out, I'm gonna set the due date for Thursday at midnight. We've covered everything. You can ask me more questions during lecture time. Actually, you can ask me in lab tomorrow if you want. Or you can ask me during lecture time on Thursday prior to submitting your file if you want to. That way it gives you a couple of extra hours if you run into snags or questions. Also send me email if you get stuck too. And I can answer some stuff by email. Other questions? All right, I will see some of you tomorrow night.